Okay, guys. So, let's say that we have this slope field, or like this differential equation right here, dy dx equals y. That's what's on your paper right now at the very top, right? It says dy dx equals y, right? And then it gives you an initial condition, y of 0 equals 2, right? So one way to approximate y of 4, if you could not, you can, but if you could not integrate this, like if it was not possible to integrate this, then one way to approximate y of 4 would be to make a tangent line at 0, 2, right? So if I had the point 0, 2, then what's my slope? 2 times x minus 0, right? So my equation would be y equals 2x plus 2, right? So if I followed this slope, you don't have to draw any of this on your paper. Just watch me. Okay, so and then if I plug in 4, I get 10, right? So y of 4 is approximately 10. Yes, this is just linear approximation.
Why is y through x value?
No, this is input. This is output. Y of 0. Like f of x. Y of 0. Yeah.
Okay.
Not y times 0.
Yeah, that makes sense.
Yeah. Because it leads to Euler's method. I'm just telling you this is one way to approximate. A lot of the C part of calculus is doing approximations for things that you cannot solve anymore. You don't write it. I'm just chill out, guys. Just absorb, enjoy the moment. Look at this soothing slope field right here. That's all you gotta do. Are you with me?
On your quiz, when we're drawing slope fields, if it's like 5 or something, and we draw it, and it just looks like, and it's not 5 really, but like it's the best that we can draw. Right?
If it's positive, like if you have a slope of 2 on the slope field and a slope of 5, I need to see that the slope of 5 is steeper than the slope of 2. That's how I'm going to judge. And if like the slope should be negative, but you drew a positive slope, then I'll take off. Or if the slope should be 0, it should be easy to tell, you know. But just make it like in comparison to your other slopes. Is it steeper or shallower or positive or negative? Does that answer your question? Okay, so Euler, genius mathematician, was like, oh, I think that there's a better way to approximate the value at 4 if I know this differential equation. All right, so this is his method. Oh, geez. Zoom. Okay, this is his method. All right, so you start with the point 0, 2, right here, 0, 2, and you do the same thing that you did with the tangent line approximation. You make a small tangent line here with the slope that you know, okay? So let's go, our tangent line at 0, 2 will be y equals, what's my slope? 2 times x minus 0, and then plus 2, right? If we move that over. Though the reason why I'm simplifying is you'll see a pattern in a little bit. Okay, so then Euler was like, cool, now I'll use it to approximate the value at another point. let's go a certain distance away. For this problem, let's do, it's going to tell you what step size to do, but let's use a step size of 1 for this problem. Okay, just to make it easy for you to see what's going on. Well, let's use the step size of 1. So now y will equal 2 times 1 minus 0 plus 2 is 4. Are you with me there? Yeah? Okay, so then he was like, cool, I'm going to go to 1, 4 now. And that's my first, I drew a tangent line up to 1, 4. Then, do you know what he said? Well, you weren't born then, but neither was I. But he said, okay, let's do another tangent line at my new point, 1, 4. So help me make my tangent line. It would be y equals, what would it be? What's my new slope at 1, 4? 4 times x minus 1 plus my y value, 4, right? So now I have a y value of 16. Oops, sorry, before we do that, now let's plug in no, 16 is not right. 8. So at 2, we are now at 8. So do you see what he did? He made like another tangent line. He's like, okay, I'll recalculate. He went and he was like, okay, here's what I'll do. I will only calculate the slope until I hit the first point. Then I'll take a look at my new slope and I'll make a tangent line with that slope up to my next point. And then then what do you think? Exactly. So then he made another tangent line at 2, 8 and said, okay, y equals 8 times x minus 2 plus 8. So y equals 8 times, and then we plug in 3, so 3 minus 2 is 1 plus 8 is equal to 16 now. That's why I had 16 in my head. So here we are at 316. And then we make one more. At 3 comma 16 is our new point. So y equals 316 x minus 3 plus 16. And then you get 32 for the tangent. Okay, any questions on what just happened here? Aaron, open your book. Hello? Open your book. Do something. Okay. Any questions? No? All right. So, do you see what he just did there? He's like, okay, let's make 4 small tangent lines with a step size of 1. So each increment, I'll reanalyze my slope of a tangent line and do a different one based on that. Okay, cool. Let's go down here and let's see how accurate we are. Because usually you can't solve this differential, but let's try to, this one you can. So if I solved for the particular solution, I'm going to want to separate and integrate, so I get 1 over y dy equals dx Everybody good there? Then we integrate. And the integral of 1 over y is natural log absolute value of y equals integral of dx is x plus c, right? Then we get rid of the natural log by exponentiating both sides. Y equals a e to the x, right? Because you still have to exponentiate the x. And then we're going to use the initial condition 0, 2 to plug in. So a equals 2, right? So my original equation is y equals 2e to the x. Okay. Let's see how accurate we are. Can somebody in your calculator plug in 2e to the 2e to the first for me? To the first. 5.4. Okay, so our first point is at 5.4. What's 2e squared?
14.7.
What's 2e cubed? Yeah, it's pretty high up here. So how's 2e to the 4th? 109 point what? 3 decimal places. Thanks. Okay. We're way off. But we're less way off than one tangent line. Right? So how do you guys are like, this method of approximation sucks. But it doesn't really. It's actually very good. Have you ever seen the movie Hidden Figures?
Yeah.
You know how she was like, oh, let's use this archaic form of math, and like she dusts off this book? That was Euler's method that she used.
Was it?
Yeah, it was.
You just watch these movies, you're like, they just keep stuff.
No, somebody actually told me when they saw the movie. They're like, oh my god, Euler's method. I was like, see, it is in everyday real life.
But if you're using it to do
massive.
something like important, wouldn't it be bad to use it just way off?
If it's the only information you have, and you don't have any other method of approximation, then it's not a bad method to do. Like, the only reason why ours is so sucky is because our step size was 1. Like, if we made our step size of 0.1, it would be, like, a lot closer. You know what I mean? Okay, so that's the answer to the next question. How can you use the same method to get better results? Smaller step size is what you want to do for that. Okay, but there's an easier way, because writing all of these, well, it's not an easier way, it's just a method to keep you from writing like a million different tangent lines. So the better method is to create a table like this that they have down here, x, y, dy. I actually I like to say dy equals, and then I like to write what dy equals. So if I had solved this for dy, what does dy equal? Y times dx. Okay, so dy equals our differential times delta x, right? And then you don't have to do this, but I've noticed a lot of people screwing up, so I'm gonna see if it helps you now. This one, in another column, you just say y new. So you should have 4 columns: x, y, dy equals y times dx, and then y new. Ignore this line right here. This line's not really here. It's just 4 columns all together. Okay. All right. So you start with the initial value that you're given, 0, 2, right? These two were given to you. So you plug those in first. And then you calculate your dy, and your dy is y times dx. So your y value here is 2. And our step size, our dx, our delta x is what? 1. Because see, our delta x is like down here, delta x. So that is 2 times, it's basically 2 times 1 is what you're doing right here.
Wait, so it's dx delta x?
The dx is delta x, yeah. The width of your step size, the size of your tangent line that you want to make. Okay. Any questions on that? All right. So notice whenever you make a tangent line, notice how it's dy is y times dx. That's this part of your tangent line. Do you see that? 4 times, and then 2 minus 1 is your delta x. And then 8 times 1, and then 16 times 1, right? So your y new is going to be dy plus y. So this is 4. So you calculate this, and then you add those together, and you get 4. 4 is your new y value, so now you're going from 1 to 4. You calculate your new dy, which is 4. Your y value is 4. Your dx is 1. So 4 times 1. So, and then your y new is adding your dy plus your y. So 4 times 1 plus 4 is 8. So now you are at 2. Sometimes I like to fill these in first, like 2, 3, 4, because I know it's a step size of 1. So now I'm at 2, 8. Then I calculate my new dy, which is 8 times my delta x, 8 times 1. 8 plus 8 is 16. And then 3, 16 is my new y value. I calculate my new dy by doing 16 times 1. 16 plus 16 is 32. So 4 is 32, and then you stop. You don't have to calculate your new dy because you're not doing a tangent line after 4. Do you see? So basically, you're doing your delta x, and this is your, right here, your dy. And you're just adding your dy plus your original y. So this is delta x, and you're adding dy. This is your delta x, and you're adding dy to your original y value, dx, and then dy. But it's all done in table form. So you could do like a whole bunch of them and not have to write a ton of tangent lines. Do you kind of get it? Yeah? Okay, let's do one more together, and then have some that you should do on your own. So here's a new differential equation. You actually cannot separate and integrate this. I don't think. Yeah, I don't think you can separate and integrate that one. So we have to use Euler's method. Starting at x equals 4 to approximate 4.2, I want 2 steps. So go x, y, what's my next one? dy. I like to write dy equals, what is it equal? X plus y times dx. Not just y, because y was the other problem. So this is x plus y dx, and then y new. This is our new y. Okay. I'm starting with 4, -1. So those are my starting values, and I want 2 steps of equal size to get to 4.2. So 2 steps means I gotta go 4 to what? To 4.2. 4.1. So 2 steps of equal size. What does that mean? If I'm going 4, 4.1, 4.2, what's my delta x? 0.1, right? All right, let's calculate. Our dy is 4 minus 1 times 0.1, which is 0.3. So -1 plus 0.3 is -0.7. Is that right? So my new y value is -0.7. Then I calculate my new dy by doing 4.1 minus 0.7 equals, what does it equal?
Why don't you multiply it?
Oh, I need to multiply it by times 0.1, thank you. So what do I get? 0.34. So -0.7 plus 0.34 is -0.36. And so 4.2. So f of 4, or 4.2, is approximately -0.36. Got it? Not too bad, right? Euler's method basically just tells you exactly what you should do. You just have to do the computations, right? That's the hardest part. Okay. Here's a worksheet. You don't have to do all of it, but you have to do. Hold on, I'll tell you what ones. Zach, does anyone sit next to you? Okay. Oh, Y new is when Y new, just think about it from a graph perspective. Oops. Y new is because you add your change in Y plus your original Y value to give you your new Y value. So this point would be dy plus where you started, plus your Y.
You found dy.
Right, so you do dy plus Y.
So in this one we had y originally as -1. And then we found dy to be 0.3. So we added -1 to get -1.
We added -1 to dy.
Yeah, so -1 plus 0.3 is 0.7.
-0.7, yeah.
And then what did you do? You found -0.7.
So -0.7 then goes here.
Yeah, but then negative 0.7 plus what was that number?
0.1. This is 0.1.
No, the new value for dy. Is that
0.34
So you added negative 0.7.
plus 0.34 is negative 0.36.
Oh, yeah.
Exactly.
Okay, yeah, I see what you were doing.
Okay. You good now?
Yeah, good thing.
All right. You gotta do number 1, 2, and 9. Sketch your solution is just like follow the slope field. Oh, no. For number 1, don't sketch your solution. You don't have to do that. But for number 9, it says sketch your solution curve. Actually sketch it on the slope field. Okay, 1, 2, what did I say? 1, 2, and 9 you must do before I give you your test back. Do you understand it?